Hidden near the heart of our galaxy burns a giant so bright it outshines millions of suns, the Pistol Star. It's one of the most luminous stars ever found in the Milky Way, and its power defies imagination. Tonight we'll uncover what makes this stellar titan so extraordinary. If you enjoy the mysteries of space, please like, subscribe and share, and tell us in the comments, what do you think could exist even brighter than the Pistol Star? Thank you for watching. Now, let's begin. The central region of the Milky Way forms a dense gravitational basin where stars, gas and dust collect inside the deep potential of the inner bulge. Mass concentration rises toward the middle, and overlapping stellar populations fill wide volumes with intertwined orbits and energetic activity. Matter in this region appears as a continuous mixture of diffuse gas molecular clouds and compact stellar groupings, arranged by gravity shear pressure and magnetic tension into filaments, knots, arcs, and layered shells. Star formation proceeds in recurring cycles as gas cools, condenses, and fragments, producing clusters of short-lived massive stars alongside numerous lower mass companions. As massive stars evolve, they return material to the surroundings through high-velocity winds and terminal mass loss events, and the released elements enrich the ambient medium. Dust grains assemble within these enriched flows, and within cool ejector-forming populations of carbon-rich and silicate-rich solids that remain mixed through both dense clouds and more rarefied gas. The combined presence of heavy elements, dust, and molecular species produces complex chemistry across a spectrum of densities and temperatures, from cold cores shielded by thick columns of gas to warm, stirred envelopes influenced by nearby energetic sources. The gravitational framework governs motions on many scales. Differential rotation introduces shear that stretches structures along preferred directions, while local self-gravity in cloud complexes can overcome shear and drive collapse. Turbulence distributes kinetic energy across a cascade of eddies, shaping the density field and regulating fragmentation. Shock fronts arise where flows meet compressing gas into thin layers and triggering further episodes of collapse. Magnetic fields thread the region and couple partially ionized gas to field lines, guiding flows along curved paths and assisting the formation of elongated filamentary structures. Cosmic rays, thermal pressure and radiation pressure contribute additional forces that help set balance within clouds and between clouds and the surroundings. The result is not equilibrium, but a persistent interplay among gravity, pressure, turbulence, and magnetic stresses, with each process rising or falling in influence depending on local conditions. Stellar content within the central region spans a wide range of ages. Long-lived lower mass stars populate the background field, adding steadily to the gravitational potential through sheer numbers, while younger cohorts appear in concentrated groupings that mark recent or ongoing formation. The energy output from massive stars influences gas on parsec to tens of parsec scales, carving cavities, piling up shells, and stirring surrounding material. Over time, these feedback loops redistribute angular momentum and seed new sites of contraction at the edges of compressed layers. The chemical state reflects repeated enrichment, so average metallicity stands higher than in the outer galaxy, and dust-to-gas ratios track that gradient. Molecules form efficiently on grain surfaces inside shielded regions, building reservoirs of molecular hydrogen and more complex species that cool gas and support further fragmentation. Thermal structure varies strongly with environment. Cold cores reach low temperatures, where cooling surpasses heating, and those pockets maintain high densities that allow gravitational binding against tidal forces from the surrounding potential. Warmer envelopes host photochemical reactions driven by energetic radiation from nearby young stars and evolved hot stars. Hotter phases occupy cavities where shocks and prior energetic events have raised temperatures and rarefied the gas. The phases coexist in pressure-modulated balance, exchanging mass along fronts and mixing layers. Dust permeates all phases, altering heating and cooling pathways by providing surfaces for chemical reactions and by storing and releasing energy during interactions with gas and radiation. Grain size distributions shift as grains coagulate in dense regions, shatter in turbulent collisions, or erode in harsh environments. These evolutionary channels reshape the population of solids, and in turn influence how gas cools contracts and forms new stars. The deep potential of the inner bulge binds these components over large timescales. Orbits crowd toward the center, shortening dynamical periods and increasing encounter rates for gas clouds and stellar systems. Cloud-cloud collisions and tidal stirring inject energy into the interstellar medium, sustaining turbulence, even as radiative cooling attempts to dissipate it. Spiral structure and bar-driven inflows channel gas inward from larger radii, raising central surface densities and supplying raw material for subsequent star formation cycles. As gas accumulates, self-gravity within dense lanes can exceed stabilizing forces, leading to further contraction and fragmentation. The resulting clusters add fresh populations of massive stars whose energetic output modifies their birth environment, continuing the feedback loop. Radiation fields inside the central region overlap from many sources and permeate wide volumes. Energy density increases near concentrations of young stars and hot evolved stars, while more diffuse backgrounds fill interstices between them. This radiation heats, dust sets ionization fractions, and participates in momentum exchange with gas through pressure gradients. Mechanical energy from winds and expanding shells combines with radiation to drive flows, evacuate cavities, and compress adjacent layers. In locations where multiple shells intersect, density rises and new cores emerge, showing how large-scale energy injection can create small-scale structure. Angular momentum transport plays a central role in the evolution of this region. Gravitational torques, magnetic braking, and viscous-like stresses in turbulent flows shift angular momentum outward, while mass drifts inward. The redistribution enables continuous replenishment of central reservoirs without requiring a single coherent stream. Over time, the accumulated effects of torques, shocks, and shear reconfigure orbits and reshape the pattern of gas lanes and stellar groupings. The region therefore maintains high densities not through static confinement, but through persistent inward supply balanced by energetic feedback and dispersal. Across all these processes, timescales span wide ranges. Freefall collapse proceeds rapidly within the densest cores, while chemical enrichment unfolds over many generations of stars. Turbulent turnover occurs on crossing times set by local velocities and sizes, and magnetic field evolution follows diffusion and reconnection times, comparable to or longer than dynamical times. Together, these clocks produce a landscape where slow secular changes coexist with brief, intense episodes. Each component stars of many ages, gas in multiple phases, dust grains across a spectrum of sizes, magnetic fields, radiation, turbulence, and gravity contributes to a composite physical state that defines the inner bulge. Within the central directions of the inner galaxy, dust density rises to markedly higher column masses than in regions farther from the bulge, and this particulate component of the interstellar medium exerts strong influence over the propagation of electromagnetic energy that originates inside the region. Dust grains within this domain consist largely of carbon-rich material, silicate-rich material, and complex mixtures that have condensed out of chemically enriched gas returned by earlier stellar generations. grain populations are not monolithic because fragmentation, coagulation, sputtering, vaporization, and accretion each act upon grain surfaces and grain interiors at different rates that depend on local temperature, gas density, radiation, field intensity, and shock frequency. Grains cluster within dense molecular lanes, but they also permeate diffuse gas volumes, forming extended particulate distributions. Across the central region, these solids function as dynamic participants in the flow of energy, because radiation transported through this environment interacts with them through scattering and absorption in wavelength-dependent ways. Shorter wavelength radiation encounters stronger interaction cross-sections, while longer wavelength radiation couples more weakly, and so energy inside the region becomes redistributed by grain population properties. The absolute abundance of grains inside the central region depends on star formation history, because high-mass stars release dust precursors within their final evolutionary phases, and those precursors become processed into grains that join the interstellar particulate population. As dust accumulates, the total geometric area of grain surfaces within a given volume increases, expanding the number of available interaction sites for radiation and gas phase constituents. These surfaces permit molecular formation pathways that would be less efficient within purely gas phase chemistry, because grain surfaces provide stable platforms where atoms can bind, react, and then release new molecules back into the gas. This catalysis modifies chemical composition and shifts cooling pathways within dense zones. Gas phase species can also freeze out onto grain mantles under sufficiently low temperatures, forming coated particles whose optical properties differ from bare grains. These coated particles contribute to the evolution of the extinction behavior of the region, because ice mantles and carbonaceous mantles modify refractive indices and therefore energy coupling efficiencies. In addition to chemical roles, grains participate in the regulation of thermal balance. Energy absorbed by grains becomes redistributed through re-emission at longer wavelengths, and this re-emission contributes to the radiative temperature structure of the medium. Meanwhile, dust-to-gas ratios inside the central region trend above the values typical of the outer disk, because repeated stellar enrichment has supplied metals into the interstellar medium across long spans of time. Radiation conditions also differ, because overlapping stellar populations generate high radiation energy densities, which heat dust and gas differently depending on density and shielding conditions. Regions closer to massive stars sustain higher dust temperatures, while shielded zones remain cooler. These temperature variations create gradients that shape material flows, because warmer regions expand more readily, while cooler regions collapse more readily under gravity if sufficiently dense. Dust grains generate friction like couplings to gas through drag forces, and those couplings influence the transfer of momentum when flows accelerate, decelerate, or collide. Thus, dust is not only a passive participant in energy transport but an active element in dynamical transfer. Grains affect ionization balance because electron sticking and desorption alter free electron fractions, and that shift in turn modifies electrical conductivity and magnetic coupling. Because magnetic fields thread the region, ionization fractions determine how strongly gas responds to magnetic pressure and magnetic tension. This modifies how turbulence cascades across spatial scales and how shock structures steepen or dissipate. Dust is therefore structurally central to multiple aspects of the region, linking chemical evolution, radiative energy, redistribution, thermal moderation, and gas magneto-hydrodynamic behavior. All of these couplings take place throughout the region itself, without reference to any vantage beyond the region. In the central directions, the cumulative column of dust along each spatial path increases strongly, and energy transport along those paths becomes shaped by particulate interactions. Because dust populations contain a spectrum of grain sizes, the net interaction strength varies continuously with wavelength, and this produces wavelength-dependent transport behavior. This wavelength dependence emerges from the intrinsic optical properties of grain material and grain size distribution, rather than from any external context. Radiation launched from hot stars, warm dust, or atomic gas within the region must traverse particulate media whose optical depth varies with frequency. If radiation encounters a grain population whose interaction cross-section is large at that wavelength energy deposition into grain, thermal reservoirs rises and subsequent re-emission shifts energy balance. Because the central region contains a rich mixture of long-lived stars and short-lived massive stars, the radiative field contains contributions from both hot sources and cooler sources, and reprocessing by dust produces a composite energy distribution within the medium. In regions where dust density becomes especially high, radiative diffusion takes place more slowly because energy must undergo repeated scattering and absorption, followed by re-emission steps to migrate through such cluttered zones. Gas near such zones experiences different heating and cooling pathways compared with more dust-poor sub-environments, and this influences rates of molecular formation, fragmentation scales during collapse, and shock propagation speeds. Dust, therefore, is a core regulator of spatial and temporal evolution. The central region of the Milky Way holds so much dust over such wide volumes that energy distribution cannot be described simply through free streaming of photons, because particulate interactions represent a dominant factor in shaping transport. Longer wavelength radiation inside the central directions of the inner galaxy experiences weaker coupling to particulate material, because interaction cross-sections scale with grain size relative to wavelength, and when wavelength surpasses the characteristic physical sizes of most solid particles, scattering efficiency declines, while absorption probability also falls. When radiation within such long wavelength bands travels through dust-rich columns, it therefore loses less energy to particulate interception. This physical fact is not a statement about a camera or an eye, and not a statement about any vantage outside the region, but simply a property of how electromagnetic energy couples to solids suspended in a chemically enriched interstellar medium. Within the central region, both short wavelength and long wavelength radiation originate from matter that emits across wide spectral bands, because heat reservoirs, chemical excitation, and thermal emission all generate energy across a physical continuum. Short wavelength energy is retrapped by grains reprocessed and re-emitted at deeper positions along the radiative transport chain, while long wavelength energy more easily migrates through particulate volumes and escapes from its local environment. This difference shapes internal propagation even before considering any external escape toward outer galactic regions. Inside the central region itself, energy distribution therefore shifts in spectral composition, as dust intercepts short wavelength energy more effectively than long wavelength energy. Grain populations with variable size distributions alter the exact transition wavelengths at which reprocessing becomes dominant, but the overall trend remains stable across many chemically evolved environments, in which dust populations contain mixtures of small and large particles with carbon-dominated or silicate-dominated compositions. In a dense cluster environment embedded in dust, rich surroundings, long wavelength energy forms deeper penetration paths because multiple scatter events that strongly affect short wavelength radiation do not recur at the same probability under long wavelength coupling rules. Therefore, in dust-rich columns, deep interior regions of the medium become more thermodynamically connected to their surroundings at long wavelengths than they are at short wavelengths. Energy gradients inside dust. Rich clouds depend on the local balance of radiative heating, thermal emission, and thermal conduction, and these depend on local grain populations and gas densities. Where particulate densities are high, long wavelength propagation channels become the most effective means for internal thermal transfer. Where particulate densities are lower, or where grain populations skew to larger average sizes, threshold wavelengths at which scattering becomes inefficient shift accordingly. These wavelength-dependent transitions are determined by intrinsic properties of matter suspended inside the region, not by any frame of interpretation from an external observer, and therefore remain intrinsic physical behaviors of the medium itself. Within the central region there are warm dust shells, warm gas filaments, and numerous hot sources that contribute short wavelength emission from their outer layers. But the fate of that short wavelength radiation depends on immediate particulate context. In thick columns, short wavelength radiation is caught, reprocessed, and re-emitted, so the emergent balance of energy will contain a larger fraction of long wavelength photons, because long wavelength transport channels enable energy to propagate farther before thermalized coupling to grains redistributes it. This behavior holds across a wide variety of dust-enriched astrophysical settings, and in the central region of the Milky Way it's established through decades of physical modelling, laboratory grain property data, and theoretical development of electromagnetic coupling to fine particulates. Within this dust-rich stellar environment, energy migrates along complex trajectories determined by particle density, grain composition, gas density, and temperature gradients. Because long wavelength energy can traverse this environment with lower optical depth, deeper layers inside the region exchange radiative energy with a broader zone of neighborhood, rather than remaining isolated behind short wavelength reprocessing barriers. Long wavelength channels therefore represent direct physical conduits for energy transport within dense particulate environments. In such zones, radiative equilibrium and thermal equilibrium depend strongly on frequency, because thermal reservoirs can remain cooler at locations where short wavelength reprocessing prevents escape of high energy radiation, while deeper layers equilibrate through long wavelength channels that enable more extended coupling across volume. Over time, these wavelength-dependent energy transfer pathways influence thermal stratification, chemical reactivity, grain mantle, growth or erosion, and molecular abundance fields, because thermal balance determines reaction rates, freeze-out rates, desorption rates, and the lifetimes of specific species. Wavelength-dependent coupling thereby becomes a regulating factor that affects physical state inside interstellar gas. The central region of the Milky Way contains sufficiently abundant dust that internal energy propagation cannot be approximated as a wavelength-independent process. Instead, transport is a multi-channel phenomenon in which short wavelength channels become locally trapped and reprocessed, while long wavelength channels travel with greater reach. These conditions influence not only radiation transport but also the dynamic responses of gas in shock fronts, expansion fronts, and collapse flows, because thermal support against gravity depends on temperature, and temperature depends on how efficiently energy can leave or enter a gas region. When long wavelength channels provide efficient radiative exchange across boundaries, cooling or heating can proceed more rapidly than if all energy channels were equally blocked. In this way, long wavelength transparency to particulate columns modifies fragmentation scales for molecular cloud collapse, because the gene's threshold depends on thermal state and therefore indirectly on radiative exchange efficiency within the environment. Deeper collapse can occur where thermal support is reduced and cluster formation is therefore influenced not only by mass density, but by the radiative transport properties of the medium itself. The fact that long-wavelength radiation possesses such transport efficiency through particulate columns therefore becomes one of the intrinsic physical determinants of how energy flows and how matter responds inside the deeply enriched central region. These wavelength-dependent phase spaces do not require a boundary for interpretation outside the region, because they are properties of the region itself, linking radiation, physics, particulate coupling and gas dynamics through intrinsic characteristics of grain populations and electromagnetic interaction rules. In the inner galaxy, there exists a region where gravitational potential deepens further than in the surrounding bulge, and within that basin stands the environment around Sagittarius, A star, a domain in which mass density, orbital velocity, dispersion, and energy densities reach values distinct from the broader central region. Gas flows in this zone do not simply drift. They accelerate and curve along trajectories shaped by the steep gravitational gradient, and differential velocities generate strong shear that stretches and distorts molecular lanes as they pass near the deepest part of the potential. Material does not remain spatially static because tidal forces increase steeply toward the center, and any cloud filament or clump that enters this environment experiences gradients in gravitational pull across its own physical extent. Dense clumps may remain coherent if internal binding forces exceed tidal differentials, but marginally bound structures can be stripped into extended streams. Stellar populations near Sagittarius A star reflect the dynamical history of the region, because stars on intersecting orbits mix, scatter and redistribute momentum across many passages. Energy densities also differ from those in less intense gravitational environments, because the kinetic energies of gas parcels increase as they fall deeper into the potential well, and collisions between such parcels can raise temperatures, alter chemical states, and create turbulent interfaces. In some zones, hot plasma exists where shocks from converging flows inject energy into the medium, while other zones remain cooler, where shielding by dense molecular matter reduces energetic interactions. These coexisting layers form a complex multi-phase environment, governed by the balance of gravity, pressure, and rotation. Magnetic fields thread these flows and tie partially ionized gas to field lines, shaping the morphology of filaments and guiding mass transport along curved trajectories that respond simultaneously to gravity and magnetic tension. Angular momentum plays a critical role in the dynamical balance, because matter that approaches too close without sufficient angular momentum plunges further inward, while matter with higher angular momentum can orbit for long durations. Redistribution of angular momentum occurs through gravitational torques, when clumps or streamers interact, or through turbulent viscosity, when eddies transfer momentum between adjacent layers, or through magnetic coupling, when field tension transfers angular momentum across distances. Over large spans of time, this redistribution enables some mass to spiral inward, while other mass carries angular momentum outward, allowing the region to evolve without requiring a single coherent stream. The environment around Sagittarius A star therefore becomes not merely a static mass reservoir, but a highly dynamic interface where the deep potential allows the conversion of gravitational energy into kinetic and thermal energy on short dynamical timescales. Gas streams that reach this zone often arrive on elongated or eccentric orbits, and their curvature under gravity shapes spiral-like streamers. In some cases, tidal compression enhances densities temporarily as gas converges along orbital paths, and such compression may alter chemical abundances, because density-dependent reactions accelerate in these brief high-density phases. Molecular species can be destroyed in hotter shocked layers and then reconstituted downstream where temperatures fall. Dust grains experience sputtering and erosion in the hottest plasma layers, while larger grains remain intact in cooler sheaths, creating a distribution of grain populations that differs from regions only a few tens of parsecs away. Dust exists not only as a tracer but as a participant in energy transfer because grain surfaces exchange energy with gas and participate in molecular formation, and these roles persist even in the gravitationally extreme environment near Sagittarius A star. The stellar population near this region includes stars of many ages because the dynamical mixing properties of the region admit stars from different formation epochs. Rapid orbital periods produce repeated passages near the center over relatively short intervals, compared with regions farther out, and each pericenter passage modifies trajectories subtly through gravitational interactions with both the deep potential and nearby stars. The high density of stars increases the probability of close encounters, and such encounters exchange energy and angular momentum between stellar orbits, producing long-term orbital diffusion. Over many cycles, this can scatter stars into different orientations, inclinations, and eccentricities. Gas in this region can also form disks or ring-like structures depending on how inflowing material aligns angular momentum vectors. These disks can become warped if torques act unevenly, and warping can induce precession. The interactions between gas flows, magnetic fields, tidal forces, and angular momentum transport shape both the geometry and the long-term stability of such structures. Feedback from stars in this region influences the surrounding medium because winds from high-mass stars inject momentum into the gas and excavate cavities, while radiation from hot stars influences ionization, balance, and chemical states. These feedback processes remain embedded within the gravitational landscape of the region around Sagittarius A star and do not override the dominant influence of gravity, but they shape the microstructure of gas flows and the thermal environment. On shorter scales, mechanical energy deposited by winds can inflate shells and drive shocks that propagate outward until they dissipate or merge with other flows. There is no requirement that such shells be isotropic because anisotropies in local density and magnetic fields can create heavily skewed expansions. On larger scales, gas settles into streamers and lanes that circulate under gravity, experience shear, and experience compression at turning points along their orbits. Because gravitational curvature dominates dynamics in this zone, energy conversion from gravitational potential into motion and then into heat occurs at high frequency. Within the inner galaxy there exists a smaller subregion that contains the Quintuplet Cluster, a concentration of massive young and middle-aged stars that occupy a portion of space in which stellar density exceeds that of the broader background around Sagittarius A star. The cluster is not a simple geometrical sphere but a spatially extended assemblage whose internal density varies with radius, whose stellar populations overlap across multiple evolutionary phases, and whose internal energy fields remain shaped by the combined outputs of the massive stars that reside inside this limited volume. Gas and dust flows interact with the gravitational potential of the cluster, and gravity from the stellar population pulls material inward, even as stellar winds and mechanical feedback push material away. Massive stars within the cluster undergo short evolutionary lifetimes, so their presence indicates recent star formation within the relevant epoch of the environment. The chemical composition of gas within and around the cluster reflects enrichment from prior stellar generations because heavy elements synthesized in the interiors of massive stars have been dispersed repeatedly into the medium. The cluster therefore contains a chemically evolved environment where dust grains enriched molecules and heavy element gas occupy overlapping spatial fields. This spatial distribution of gas surrounding the cluster includes filamentary lanes, clumps and shells, and these structures form under combined actions of gravitational binding, thermal pressure, magnetic tension, and mechanical feedback from the stars. Radiative energy fields inside the cluster span wide ranges of intensity because individual massive stars contribute extreme luminosities that overlap to form composite radiation fields across the entire object. These radiation conditions affect dust grain temperatures and influence the survival lifetimes of molecular species inside both dense cloud cores and more diffuse envelopes. The mechanical energy fields of the cluster arise from stellar winds that eject mass at significant speeds. An interaction between such winds and surrounding gas produces shock surfaces and compressed layers of material. These compressed layers can fragment and contribute new seeds for subsequent gravitational collapse if conditions satisfy appropriate thresholds of thermal balance and density. The cluster contains a mixture of hot evolved stars, massive main sequence stars, and less massive stars that formed in the same general time frame. The presence of such populations generates a broad luminosity function across the cluster, and the combined light of these stars contributes to the overall energy density within the region. Magnetic fields thread the cluster environment and influence gas transport by coupling partially ionized material to field lines. These field lines shape filamentary structures and modify the flow of gas across the volume. Turbulent cascades within the cluster contribute to velocity dispersion and influence fragmentation scales within compressed gas layers. Angular momentum distribution determines how gas aligns within filaments or disks, because flows with insufficient angular momentum plunge inward and dissipate energy, while flows with higher angular momentum remain stable along curved orbits. The cluster contains dust grains, whose populations reflect the complex processing history of this region. Grain size distributions shift continuously under the influence of grain growth in dense regions, grain erosion in high-temperature plasma zones, and grain collision fragmentation within turbulent flows. Grain surfaces act as catalytic sites for the formation of the molecules that would not readily form in purely gas phase pathways. These molecules can freeze out onto grain surfaces at sufficiently low temperatures, forming mantles that alter optical properties. Dust and gas phases therefore remain dynamically interlinked, because dust plays a role in energy transport cooling processes and chemical evolution within the cluster environment. Radiation fields from the massive stars alter ionization fractions within gas, and ionization fractions determine electrical conductivity. Conductivity in turn determines how gas couples to magnetic fields, and thus magnetic forces contribute to shaping gas morphology. Feedback from massive stars injects momentum into the medium, creating bubble shells, cavities, and shock surfaces. Where these surfaces intersect, gas densities rise, and gravitational binding may become strong enough to drive local collapse. In this way, the cluster environment creates feedback-regulated star formation cycles. The large-scale gravitational potential of the cluster interacts with the gravitational potential of the central region. As a result, orbital trajectories of gas and dust within the cluster are influenced by external forces as well as internal ones, and the balance between external tidal forces and internal gravitational binding determines whether the cluster retains gas or loses it to the broader environment. Temperature fields vary across the cluster volume because nearby massive stars generate hotter regions, while shielded pockets retain cooler conditions. Variations in thermal structure influence rates of molecular formation, rates of dust mantle growth, and rates of freeze-out of gas phase species. Over time, chemical complexity expands as molecules accumulate within cold cloud cores and then desorb back into gas when heated. Dynamical interactions inside the cluster depend on stellar evolution as well. As massive stars age, they pass through short-lived evolutionary phases that drive extreme mass loss. These mass loss events shape the surrounding medium and alter local density fields. Dust grains may form inside these ejecta, and those grains then join the general particulate population. Stellar crowding inside the Quintuplet Cluster produces a distinctive spatial regime, where many massive stars occupy volumes that in less dense star-forming complexes would contain far fewer individual sources. The combination of short-lived massive stars, intermediate mass stars, and less massive stars produces overlapping gravitational influence fields because the separation between neighbouring systems is small enough that the gravitational acceleration from one source is not negligible at the position of another. Orbital trajectories therefore do not behave like isolated two-body orbits, but instead evolve under combined multipole gravitational fields from many actors simultaneously. Dynamical relaxation cannot fully proceed because the lifetimes of the most massive stars are short. Massive stars evolve through their internal nuclear burning stages rapidly, so they reach late phases of their stellar lifetimes, on timescales shorter than the times required for full gravitational thermalization to distribute kinetic energy uniformly among cluster members. As a result, stars within the Quintuplet Cluster retain velocity dispersions that reflect their formation environment and subsequent close gravitational interactions. Over many orbital cycles, stars can exchange angular momentum and kinetic energy, but dynamical equilibrium does not fully form before the most massive stars complete their lifetimes and inject processed material back into the environment. Gas streams inside this cluster, scale gravitational field do not behave like laminar flows. Gas parcels accelerate, decelerate, and shear as they pass close to massive systems or compact remnants. Pressure gradients, gravitational curvature, and magnetic tension can redirect flows from initial vectors into curved pathways. Locations where gas flows converge can produce transient overdensity zones, where density increases sharply. If such overdensity zones cross critical density thresholds, and if thermal support is insufficient, collapse can proceed locally, but local star-forming events are constrained by feedback from nearby massive stars, which inject mechanical energy through winds that sweep gas aside or compress it into narrow shells. These mechanical winds from massive stars collide with each other, where their expansion cones intersect. In such collision zones, shock surfaces form, and those shock surfaces heat gas to high temperatures. Molecules that survive in cooler zones can be destroyed inside shock-heated volumes, but downstream from shocks deformation can occur as the gas radiatively cools. Dust grains near shock surfaces can experience erosion, sputtering, mantle stripping, and fragmentation. Grain size distributions therefore evolve differently across the cluster, because dust in cooler, denser regions can retain mantles and sometimes even coagulate into larger particles, while dust in hotter, shocked regions can fragment or lose its surface layers. This spatial variation in grain population affects chemical states because grain surfaces provide catalytic sites for molecular formation, and in regions where grain populations have been eroded, surface area decreases and catalytic pathways shift. Radiation from massive stars influences temperature ionization and chemical abundances. Radiation fields overlap in this crowded cluster, forming composite fields with intensity gradients that vary across short distances. Gas in regions exposed to intense radiation can become highly ionized, while shielded pockets inside dense materials remain neutral or weakly ionized. Ionization fractions influence electrical conductivity. Electrical conductivity influences magnetic coupling. Magnetic coupling determines how gas flows respond to magnetic field lines. Therefore, magnetic fields shape filamentary structures inside the cluster, guiding plasma along certain trajectories more readily than along others. Gas cannot move freely through magnetic fields if it is strongly coupled to those fields. Instead, it flows along channels defined by field geometry. Turbulence inside the cluster is not isotropic because magnetic fields modify energy cascades. Turbulence cascades through eddies that align preferentially with magnetic field directions, so velocity dispersion becomes anisotropic. Over time, small-scale eddies can transfer energy to larger modes or dissipate energy through radiative cooling and viscous heating. The combination of stellar winds, radiation pressure, magnetic tension, turbulent viscosity and gravitational potential produces an environment in which gas structures evolve continuously. Density fields shift, expand, collapse, fragment, and diffuse as different processes dominate at different timescales and locations. Dust grains follow gas motions because drag forces couple solids to gaseous flows. Grain surface temperatures fluctuate according to exposure to radiation from nearby massive stars. In hotter zones, molecules desorb into gas phase. In colder shielded zones, molecules freeze onto grain surfaces. The cluster environment therefore contains chemical gradients that reflect temperature gradients. Grain evolution modifies optical properties, and optical properties modify radiative energy coupling efficiencies. This feedback loop between radiation and particulate evolution acts as a regulatory mechanism on small scales. Angular momentum redistribution occurs through many channels. Stellar encounters exchange orbital angular momentum. Turbulent viscosity redistributes angular momentum across gas layers. Magnetic braking transfers angular momentum from gas to field lines and then to broader environments. Over many cycles, these processes alter orbital inclinations, eccentricities, and semi-major axes of both stars and gas substructures. Because massive stars evolve rapidly, they introduce sudden mechanical changes into the environment when they shed mass at high rates. Such mass loss events introduce fresh dust and heavy elements into the cluster medium. After such events, the surrounding environment acquires new particulate distributions and new opacity fields. Local environments inside the Quintuplet Cluster display subregions in which gas density rises above the cluster average, and within these subregions, feedback from massive stars has carved filaments, compressed ridges, diffuse shells and irregular cavities. These structures define the immediate physical surroundings that precede the narrower zone in which the object known as pistil star is embedded. Yet this section must remain at the level of the cluster local medium as a continuous physical domain without identifying or describing any individual stellar source. Gas near the highest density ridges exists in multiple phases that coexist within small physical volumes because molecular cores, warm envelopes, and hotter sheaths interact continuously across short spatial boundaries. Compression by winds from massive stars has stacked layers of gas into thin shells, and such shells can wrap around several different mass loss regions at once, because feedback from multiple massive actors overlaps. The density contrasts in such shells can exceed the density of the extended filaments by large factors, producing spatial gradients that drive shear at their boundaries. The grain populations in these shells evolve differently from the grain populations inside cooler, more shielded cores because erosion is stronger, where wind ram pressure and shock heating are substantial, while grain coagulation is more efficient in cold cores. The distribution of dust and heavy element molecules inside the cluster medium therefore records a spatially varying chemical history. Within these compressed ridges, the gas can accumulate heavy enough columns that gravitational binding can temporarily compete against dispersive feedback forces, but long-term stability remains rare because mechanical energy injection from surrounding massive stars alters pressure fields before equilibrium holds. Warm molecular envelopes separate dense cores and shocked sheaths, and their temperatures fluctuate according to radiative exposure. Gradients in temperature set gradients in chemical state. Because reaction rates freeze out efficiencies, photodissociation, cross-sections and desorption processes depend on local thermal conditions. Inside the cluster environment, the grain surface population remains chemically active. Molecular species attach to grain surfaces where temperatures are low, and surfaces act as catalytic platforms for association reactions that produce complex molecules. When these grain surfaces enter warmer environments, desorption releases these molecules back into the gas phase, thereby modifying local abundance and shifting chemical balance. The spatial arrangement of gas in this layer is therefore a composite of variable density ridges, cavities, shock fronts, filaments, and diffuse envelopes. Warm dust radiates through long wavelength channels that remain effective at carrying internal energy within this particulate medium. Long wavelength transport allows thermal information to propagate across longer distances before being reprocessed into new emissions. The combination of long wavelength transparency and short wavelength trapping produces frequency-dependent thermal stratification in the medium. Under conditions of strong compression near shock surfaces, the gas reaches temperatures that produce ionization fractions high enough to modify the interaction between magnetic fields and the partially ionized medium. Because interstellar magnetic fields thread this region, they constrain the direction in which ionized gas parcels can travel. Eddies in turbulent flows remain elongated along magnetic field lines, producing anisotropic turbulence where energy cascades along different slopes than in non-magnetized turbulence. The local medium of the Quintuplet Cluster therefore exhibits turbulence that cannot be approximated as isotropic hydrodynamic turbulence. Instead, magnetic tension shapes turbulence, anisotropy, and this anisotropy shapes how structures form and evolve. Filaments inside this cluster environment arise partly through gravitational contraction and partly through magnetic channeling. Gravitational contraction along field-aligned filaments can produce elongated overdensity structures whose axes coincide with the orientation of the magnetic field. These elongated filaments can become nurseries for attached cold cores, but any developing collapse pathway remains influenced by the feedback conditions present in the cluster. Winds from massive stars create expanding bubbles that intersect with these filaments. When multiple bubble surfaces intersect, they produce overlapping shock fronts that can drive new compression zones. As these multiple feedback processes operate simultaneously, within the cluster shells collide, shear flows develop at the boundaries between distinct momentum streams, and layering occurs in which gas moves in opposite directions along adjacent sheets. Angular momentum distribution at this subregion scale becomes a function of shear boundary interactions. Local torques produced by velocity gradients can transfer angular momentum between neighboring sheets or between sheets and adjoining filaments. Turbulent viscosity distributes angular momentum across scales by transferring momentum between eddies, and magnetic tension redistributes angular momentum by coupling rotational motion to field geometry. Local evolution therefore does not proceed through simple radial inflow or outflow, but through a network of flows that interlock. The chemical and thermal conditions in this subregion fluctuate as new feedback episodes occur, because each episode introduces new mass loss changes, density fields injects mechanical energy, and modifies temperature gradients. Because the lifetimes of massive stars remain short, their late evolutionary phases produce sudden increases in mass loss rate, and these increases inject fresh particulate matter into the local medium. Dust formed in these later phases contains high fractions of processed heavy elements. That dust expands outward and eventually mixes with older particulate material. Grain surfaces change composition as these new grains enter the environment. The new dust may be warmer or may carry mantles that differ from earlier chemical cycles. The addition of new grains changes the total particulate cross-section per unit volume, changing radiative coupling and altering the thermal balance of nearby material. Dust therefore participates in the regulation of future energy redistribution inside the subregion. Because dust couples to gas changes in grain, populations alter gas drag and thereby help shape gas distributions. The cluster medium within this subregion therefore includes a dynamic particulate system whose composition and size distribution are continuously being reshaped. This medium contains shells that expand filaments that stretch cavities that widen, and cores that contract. Feedback cycles continue because as soon as one massive star evolves through a late phase and ejects, mass new shocks form and newly created shells will push outward until they interact with boundaries shaped by older feedback cycles. The interactions of these shells carve new pathways through the medium, erasing older filaments, consolidating fresh layers, and creating transitional substructures in which the temperature density, molecular abundance, and magnetic alignment differ from the surrounding gas. Within this narrower portion of the Quintuplet Cluster local medium, the gas and dust distribution forms a circumscribed environment that contains an expanding shell system produced by powerful mass loss activity that occurred earlier in the life history of the massive source located inside this domain. The shell configuration is not a thin spherical membrane, but instead a three-dimensional volume composed of non-uniform layers with density contrasts that vary across angular directions, because both the mass loss that created the shells and the ambient medium through which these shells expand possessed internal asymmetries. Expansion did not advance into a vacuum. It advanced into a particulate-rich interstellar material that offered resistance through gas pressure, magnetic tension, drag forces on grains, and dynamical competition from neighbouring flows that were themselves shaped by the broader feedback lattice of the Quintuplet Cluster. Shell thickness differs along different directions, because expansion along lower density channels proceeded with higher local velocity than expansion along denser ridges. Magnetic field morphology also influenced shell curvature because partially ionized gas responded to field-aligned tension in ways that channeled momentum differently along each axis. Thermal structure inside the shells varies with distance from the initial momentum injection region. Outer edges of the shells contain cooler layers, where temperature has fallen after adiabatic expansion and radiative cooling, while inner layers remain warmer because they remain nearer to the sites at which kinetic energy was converted into mechanical expansion. Chemical abundances inside these shells differ from cluster ambient values because the material ejected during the mass loss episode contained processed elements synthesized in stellar interior phases. Heavy elements such as carbon, nitrogen, and oxygen therefore exist in enhanced abundance inside these shell structures, and dust grains that condensed in the ejected material contain correspondingly enriched compositions. As those grains expanded outward, they entered collision zones where pre-existing cluster medium gas slowed their motion, and drag forces redistributed momentum across grain and gas components. Grain surface evolution continues along this shell volume because different parcels encounter different thermal conditions. In warmer inner layers, surface coats can evaporate or sublimate, exposing crystalline or amorphous cores. In cooler outer layers, gas molecules accumulate onto surfaces and form ice mantles. These mantle growth pathways change optical properties of grains and therefore alter how radiative energy couples to the particulate medium. The gas density profile across the shells varies because expansion into an inhomogeneous cluster environment produced compression in some zones and stretching in others. Regions of high compression formed where the expanding shock front encountered dense filaments. Molecular species in those zones underwent shock-driven heating and partial dissociation before cooling produced reformation downstream. The shell system thus contains chemical signatures of both destruction and regeneration. Overlapping radiation fields from the cluster influence ionization states of these shells. Where radiation intensity is high, gas becomes partially ionized and couples more tightly to magnetic fields. Where radiation intensity is shielded by dust and molecular material, gas remains more neutral and decouples from magnetic fields, altering the direction of mass transport. These ionization gradients further sculpt the shell geometry by regulating whether gas parcels can cross magnetic field lines freely or must flow along field-aligned channels. Turbulence influences the internal morphology of the shell volumes. Shock-induced turbulence in compressed zones cascades into smaller eddies, distributing energy across scales and enhancing mixing between processed ejecta and ambient cluster material. Magnetic fields influence these cascades, producing nisotropic, turbulent structures that extend preferentially along field-aligned direction vectors. Because the lifetime of massive stars that can drive such large outflow events is short, the shell system does not represent a static equilibrium configuration, but a transient structure that evolves as the internal pressure inside the shell drops as the surrounding ambient medium reshapes the boundaries, as grains evolve and as chemical exchanges take place along interfaces. Over time, the shell system continues to move outward from its origin point inside this local medium. The momentum that drives this outward motion gradually diminishes as drag forces and radiative losses drain kinetic energy. The degree to which the shells remain coherent depends on both internal pressure support and external shear. Shear arises because gas flows inside this part of the cluster do not move uniformly. Adjacent streams can carry different velocities or momentum directions, and those differences tear into shells along streaks, creating elongated cavities that then act as new pathways for expansion. Shell fragments can detach and become separate moving structures that drift through the medium, carrying with them chemical signatures of the mass loss episode that launched them. Grain populations inside these fragments may differ significantly from the grain populations in the cluster background because they carry a record of nucleosynthetic processing. Grain collision rates change along their path because turbulent viscosity density gradients and velocity shear alter encounter frequencies. Shatter events reduce large grains to small fragments, while coagulation events in cold pockets produce larger grains from smaller precursors. In this way, the particulate population inside these shells continues to evolve long after initial ejection. The surrounding environment contains regions where the expanding shells interact with winds from other massive stars, and collision between outflow shells and external winds can create secondary shock surfaces. Secondary shocks heat gas-destroy molecules, strip grain mantles, and push material sideways along new channels. Such interactions produce intricate layering patterns within the shell system. Because heavy element-enriched material occupies these shells, their continued expansion enriches the surrounding medium in a patchwork pattern, imprinting non-uniform chemical gradients across local cluster scales. Radiation fields influence long-term evolution. by heating grains and gas, thereby altering thermal balance. Grains that retain mantles at lower temperatures contribute to cooling through vibrational and rotational emission mechanisms. Grains whose mantles have been stripped in hotter environments interact differently with radiation, and therefore reflect different smoothing rates for energy balance. The shell system thus functions as a chemical radiative, mechanical and particulate processor embedded inside the cluster medium. The existence of these expanding shells marks a distinct physical layer that lies closer to an individual massive source than the broader cluster local medium. But this section concludes at the scale of the shells themselves and does not yet enter the specific structural layers of the stellar wind zone that lies immediately interior to this volume. Within the region interior to the expanding shell system lies a domain defined by continuous mass outflow from the massive star that launched those shells, and this domain consists of a stellar wind zone in which matter departs the outer stellar layers in a sustained stream. This wind emerges from physical processes in which radiation field pressure thermal gradients and line-driven acceleration together overcome gravitational binding at the stellar surface, and the result is a constant outward flux of material. The momentum of this wind carries energy and mass into the surrounding medium, and because this wind zone represents the immediate layer between the stellar atmosphere and the previously described shell system, it behaves as a dynamic transitional boundary through which internal processes directly influence the environment outside. The wind does not exhibit a constant scalar profile in every evolutionary phase of the star. Instead, the mass loss rate varies with time because the internal conditions of extremely massive stars change as nuclear fusion stages progress and as envelope structure reorganizes due to instabilities associated with the luminous blue variable category. The luminous blue variable class is characterized by variability that includes steady wind phases and episodic eruptions, in which mass loss rates temporarily increase far beyond baseline wind outflow. During stable wind-dominated intervals, outflow remains dominated by radiative acceleration of ions inside the upper atmospheric layers, and the result is a continuous stream of gas that exits the outer boundary of the stellar atmosphere. Line opacity modulates the coupling between radiation and ions, so the wind speed and mass flux depend on internal chemical composition and on ionization states of metals inside the envelope. When envelope temperature and chemical composition lead to efficient line driving, radiative pressure can accelerate particles to high velocities, resulting in powerful continuous mass loss. In contrast, during episodic phases, internal instabilities associated with changes in envelope structure, opacity shifts or thermal runaway events can generate sudden increases in mass ejection. These episodic outflows produce mass loading at rates far above steady wind values, and because the density of outflowing material rises sharply in those windows, collisions within the outgoing stream generate shock compression. These compression zones can seed the formation of partially detached layers that later contribute to the multi-shell architecture outside. The regular wind carries metals synthesized inside the star. Over long intervals, these continuous exports set baseline enrichment of the surrounding region, while episodic eruptions produce discrete events with more dramatic additions of processed material. Gas leaving the star through the wind zone contains ions capable of cooling radiatively at larger distances from the surface, and as cooling proceeds, material condenses into particulate forms that later evolve into dust grains. This conversion from gas to grain does not occur uniformly because the wind zone contains gradients in temperature and density. Closer to the star, temperatures remain too high for condensation to occur, so matter remains in gas phase. At slightly greater radii, where expansion reduces temperature and density condensation becomes possible along energetic pathways that build small seed particles. As wind matter continues to accelerate outward, further cooling permits mantle formation on seed particles, leading to grain growth. The wind zone therefore functions as a nursery for particulate creation. The wind zone also incorporates interactions between mechanical acceleration and magnetic fields. If magnetic fields thread the stellar atmosphere, partial coupling between ionized gas and magnetic field geometry results in anisotropic flow patterns in which wind velocities differ along different directions. Turbulence generated by shear within the outflow modifies the distribution of shock surfaces and may influence condensation rates by locally altering density and temperature fields. In luminous blue variable wind zones, the radial mass flux and outflow velocity evolve as the star advances through nuclear burning stages. As internal temperature gradients rise or envelope opacity changes due to chemical evolution inside the stellar interior, radiative pressure coupling intensifies or weakens. These changes shift mass loss rates and wind velocity. Over time, variations in wind conditions produce layers whose density and composition differ from earlier wind outputs, and those differences persist as fossil records within the stratified shell system farther out. The wind zone therefore contains physical memory of internal stellar history. The matter in this zone undergoes continuous acceleration until the dynamic pressure of the wind meets environmental resistance at the boundary where wind ram pressure equals the pressure of the ambient cluster medium. That interface sets a contact discontinuity and defines where interior wind becomes exterior flow, interacting with the shell system. This dynamic interface can shift outward or inward depending on fluctuations in outflow strength. During episodic mass loss events, the interface can move outward abruptly because mass flux rises enough to overcome external resistance. During lower mass flux intervals, the interface migrates inward because ram pressure weakens, because the wind zone exports processed heavy elements. This layer acts as a precursor to chemical enrichment of surrounding space. Ionization levels remain high close to the star but decline with distance, and as gas recombines, it transitions into more neutral states that support molecular formation when cooling becomes sufficient. Particles created in this zone later join the shells, and the larger cluster medium and grain surface properties trace the conditions under which they formed. These interior outflow physics define the distinction between steady wind conditions and episodic mass loss phases in luminous blue variable evolution. Below the wind zone lies an outer atmospheric layer in which the stellar surface constitutes the boundary from which emergent radiation originates and from which mass loss processes begin their ascent through acceleration. This region can be described as a photospheric domain because it encompasses the depth range within which outward moving photons escape, without undergoing further thermalization cycles when passing upward. The temperature in this atmospheric zone remains high enough to maintain ionized metals whose line opacities set the strength of radiative acceleration farther out, and the density in this layer falls rapidly with altitude above the radius, at which continuum optical depth approaches unit values. The gradient in pressure through this layer is steep because hydrostatic balance near the surface links internal pressure support to the gravitational binding force exerted upon the plasma, and the pressure field therefore changes sharply with radial coordinate. Gas here consists primarily of hydrogen and helium, with heavy element trace fractions that reflect internal nucleosynthetic history. The heavy element abundances influence opacity, because metals contribute significantly to line absorption at these temperatures, and line absorption affects momentum transfer between radiation fields and gas. The luminous blue variable classification arises in part from the luminosity of these stars because extremely high radiant flux intensities at the surface drive mass loss processes that are sensitive to envelope structure. The envelope does not remain fixed indefinitely because internal fusion advancing through heavier chains alters energy production rates and modifies envelope heating. The result is that the density and temperature profiles of the atmospheric layers can change on timescales shorter than the total evolutionary timescale of the star. Variations in line opacity within this atmospheric region originate from changes in ionization balance that result from dynamic changes in temperature and density. When line opacity increases, radiation couples more strongly to gas, which increases acceleration potential. When line opacity decreases, radiation coupling weakens and mass loss may subside into a lower baseline regime. The outermost atmospheric cells radiate energy that has propagated outward from deeper zones where fusion occurs. Radiative transfer through this layer is not uniform because spectral lines contribute to absorption pockets. These absorption pockets represent frequencies at which energy transport slows relative to continuum channels. The emergent spectrum therefore displays features that correspond to transitions of specific ions, and these features depend on temperature density and chemical abundance within the photospheric domain. Turbulent motions in the outer atmosphere generate inhomogeneous velocity fields. These fields broaden spectral features because Doppler shifts smear out transitions in frequency space. Such velocity fields reflect convective overshoot in zones where inefficient radiative transport alone cannot remove energy quickly enough to maintain uniform thermal gradients. Convection in luminous blue variables may contribute to temporal variability in atmospheric structure, and this variability can propagate upward to influence wind-based conditions. Differences in local temperature across the photospheric surface cause brightness variations in which some patches contribute more radiative flux to the wind-launching regions than others. These spatial variations drive anisotropic line driving. The atmospheric geometry can depart from spherical symmetry because rotation can flatten the star-producing equatorial bulging and polar compression. Such rotational flattening modifies effective gravity across latitudes. Effective gravity is lower at the equator than at the poles when centrifugal forces act against gravity, and this gradient in effective gravity influences mass loss rate distribution by latitude. Enhanced equatorial wind outflow may originate from regions where effective gravity is weakest. Conversely, polar winds may emerge with different velocities. Magnetic fields closer to the surface further modulate these distributions by guiding charged flows along curved paths. Across this atmospheric zone, thermodynamic equilibrium does not hold globally. Instead, local parcels adjust to changing physical conditions generated by internal structural evolution. The energy flux crossing this layer reflects the output of fusion deeper inside. That fusion produces heavy elements, and convective circulation may dredge up some of those elements into envelope layers. Such dredge-up events alter the chemical composition of the outer atmosphere. That chemical modification influences opacity, and opacity influences radiative acceleration. Over long intervals, these chains of feedback modify mass loss structures, and by extension the morphology of windborne shells in the surrounding medium. The photospheric region also contains sound waves generated by convection and internal pulsation. These waves propagate outward, steepen, break, and deposit energy in upper atmospheric zones, adding to mechanical driving energy in the wind-launching region. Wave-driven energy transfer represents an additional channel alongside radiative momentum transfer, and the relative contribution of these channels depends on internal structural parameters of the star. The outer atmosphere therefore reflects multiple couplings, coupling between radiative flux and ions through line absorption, coupling between convective overshoot and velocity fields, coupling between rotational flattening and surface gravity distribution, coupling between magnetic field topology and charged flow geometry, and coupling between chemical abundance changes and opacity modulation. These couplings together produce a dynamic atmospheric system that directly binds the interior fusion engine to the exterior wind zone. All emergent mass loss processes pass through this layer because mass cannot escape from deeper areas without transiting through these atmospheric heights. This region therefore constitutes the internally contiguous layer immediately interior to the wind outflow zone and immediately exterior to deeper subphotospheric layers. The physical state of this zone sets boundary conditions for mass flux radiation distribution, chemical signature of ejected matter, condensate precursor composition, and velocity fields that seed grain formation pathways farther out. Beneath the photospheric boundary lies a zone in which energy does not travel freely, but migrates outward through radiative diffusion, and at greater depths where opacity rises through convection, in which large-scale mass motions transport thermal energy across radial layers. In extremely luminous massive stars, the luminosity is so high that radiation pressure contributes a substantial fraction of the total outward force, and this modifies the stratification of density and temperature through these energy transport layers. Radiative diffusion functions through photon scattering and absorption on ions, atoms, and free electrons, and the cumulative effect of many successive scatterings lengthens the path that radiation must take to cross a given depth. At densities high enough to produce strong opacity, photons do not transfer energy efficiently through direct ballistic transit. Instead, energy remains stored temporarily in the matter until re-emission events move it incrementally outward. As depth increases, temperature rises because nuclear energy production occurs deeper than these layers, and because radiation that attempts to propagate outward remains trapped long enough to create steep temperature gradients. Chemical composition in these layers consists primarily of hydrogen and helium, with increasing fractions of heavier metals that reflect the nuclear fusion stages already completed. Metallicity affects opacity, because many ions of heavier elements possess numerous transitions that contribute to line opacity, and line opacity significantly influences radiative diffusion efficiency. As deeper layers undergo fusion of heavier species, the chemical makeup of partially processed material modifies energy transport behavior. Convection begins where radiative diffusion alone cannot remove energy at rates sufficient to maintain thermal gradients below the threshold for buoyant instability. When that threshold is crossed, ascending parcels of hot material rise and displace cooler descending parcels. This bulk motion permits energy to move outward more effectively than through radiative scattering alone. In these conditions, convection reduces the local temperature gradient because energy can escape through mass transport rather than radiative exchange. The transition between predominantly radiative layers and predominantly convective layers depends on opacity, local temperature, and density. In extremely luminous blue variable stars, radiation pressure contributes to buoyancy forces, and convection can extend closer to the photospheric boundary than in stars of lower luminosity. Because radiation pressure is strong outward, thermal gradients approach stability thresholds at which convection can begin. Energy therefore moves outward through alternating intervals of radiative and convective dominance. In addition, wave-driven energy transport accompanies convection. Convective plumes generate internal gravity waves and acoustic waves that propagate into higher layers. These waves carry energy and momentum, and they deposit that energy in zones where their amplitudes steepen, break, or dissipate. This deposition modifies the thermal structure of upper atmospheric layers by injecting mechanical energy into them. Magnetic fields that reach into these energy transport zones influence convective geometry because magnetic tension resists certain directions of motion more strongly than others, and this bias introduces anisotropies in convective flows. Turbulence within convective cells evolves through cascades that distribute kinetic energy from large scales to smaller scales. The turbulent cascade continues down to scales where viscosity dissipates energy as heat. Because these regions contain ionized plasma, viscosity depends on charged particle collisions and magnetic coupling. The presence of magnetic fields modifies dissipation pathways, thereby altering how energy flows through different scales. Radiation pressure also modifies mixing, because buoyancy is not determined solely by thermal gradients, but by total pressure gradients, and thus convection depth. Mixing intensity and mass flux vary depending on the local ratio of radiation pressure to gas pressure. When radiation pressure dominates strongly, stratification becomes delicate and density inversions can occur. In such cases, interior pressure rises in deeper layers faster than in intermediate layers, setting up conditions for envelope inflation, in which the outer radius increases temporarily. Envelope inflation can alter the local temperature profile and therefore alter opacity. These opacity changes feed back into energy transport because line absorption depends on both temperature and ionization state. In extremely luminous stars such as those that fall within the luminous blue variable category, this feedback contributes to episodes in which envelope layers can become unstable. In some circumstances, local opacity increases enough to trap additional radiation temporarily. When sufficient energy is stored in a thin radial layer, that layer can expand and cool, changing ionization balance again, and thereby reducing opacity. Such opacity cycles can drive pulsation-like behavior. Pulsation modulates convective flows. Pulsation also modulates wave-driven energy transport. Over periods that exceed dynamical timescales but remain shorter than evolutionary timescales, this envelope feedback can reorganize local convection geometry. Convection in these energy transport layers also mixes chemical species. When convective cells penetrate deeper zones where fusion has produced heavier metals, they can dredge up enriched material and deposit it closer to outer radii. This enrichment influences line opacity in those layers and thus influences radiative acceleration farther out. Because radiation pressure coupling efficiency depends on metallicity feedback, from convective mixing alters mass loss patterns by changing coupling efficiencies in the atmospheric and wind-launching domains above. Over longer intervals, this iterative enrichment influences the chemical composition of outflow. The energy transport layers therefore remain not only conduits for energy flux, but regulators of mass loss morphology. Small variations in opacity can produce significant changes in radiative acceleration. In extremely luminous massive stars, this sensitivity results in envelope structures that lie close to the threshold between hydrostatic stability and expansion driven by internal radiation pressure. When envelope material expands, it cools, becomes less ionized, and undergoes opacity changes that can reverse the expansion. Beneath the energy transport layers lie regions where thermonuclear fusion of progressively heavier elements proceeds, and in extremely massive stars such as those that fall within the luminous blue variable category, this interior fusion sequence unfolds on accelerated evolutionary timescales, because the amount of mass present at birth sets central temperatures and densities to levels at which nuclear reaction chains advance rapidly. Hydrogen fusion through proton capture establishes the earlier stage of interior energy generation, and as hydrogen within the core becomes depleted, the fusion of helium into carbon begins. Fusion of helium requires higher temperatures and densities than hydrogen fusion, and because such conditions are present in these interiors, the conversion of helium into heavier nuclei proceeds efficiently. Subsequent burning stages transform carbon into neon, neon into oxygen, oxygen into silicon, and silicon into still heavier nuclei, and each stage occurs under more extreme conditions than the preceding one. The fusion of heavier elements produces energy by converting a fraction of mass into radiation, and that radiation moves outward through the radiative, diffusion, convection, and wave transport layers described earlier. Because each successive burning stage operates over a smaller fraction of total time, the interior chemical composition changes over increasingly shorter durations. Extremely massive stars evolve rapidly because nuclear reaction rates depend strongly on temperature, and small increases in central temperature produce large increases in reaction rate. Metallicity also influences the fusion pathways, because heavier nuclei in a stellar core alter how energy is released through nuclear channels. In extremely massive luminous blue variable stars, the central temperature can reach values high enough to sustain advanced burning stages during relatively early intervals of total lifetime. The fusion chain continues only up to iron group nuclei, because fusion beyond iron does not produce net energy. When central material becomes dominated by iron group elements, energy generation through fusion cannot proceed efficiently, and interior evolution approaches a stage at which gravitational collapse becomes unavoidable. However, the local description of this section does not enter collapse behavior, because collapse represents a possible future scenario that depends on final mass loss history and metallicity, and those outcomes remain uncertain. Instead, the description remains bounded at the level of present interior fusion behavior. Fusion of heavier elements releases neutrinos along with photons. Neutrinos escape the star almost without interaction, and the loss of energy through neutrinos contributes to cooling deep within the stellar core. Because neutrinos remove energy without contributing to outward pressure, support their emission influences thermal balance in deeper layers. The fusion interior therefore contains a complex interplay between radiative energy generation, radiative energy loss, neutrino cooling, and energy redistribution through convection. Convection mixes partially processed nuclear material, because rising plumes of hot plasma transport heavy nuclei outward from deeper layers. This mixing reduces composition gradients. In extremely massive stars, composition gradients change rapidly because fusion occurs quickly, and convection erases sharp boundaries between burning shells. Nuclear burning stages can form semi-overlapping shells, because convective mixing reduces the separation between zones that fusion theory, when treated in simplified static form, would present as distinct layers. Turbulence further blurs these boundaries. Waves generated by convective motions propagate upward and downward from burning layers and carry energy and momentum across radial boundaries. In these interiors, wave breaking can deposit energy locally altering thermal gradients. Because these layers exist under strong gravitational confinement near the deepest region of the star density values, reach high magnitudes. Radiation pressure contributes significantly to supporting mass against gravity. Gas pressure also contributes. The ratio between radiation pressure and gas pressure depends on temperature and density. As temperature rises in deeper layers, radiation pressure can dominate, and in these regimes, buoyant instabilities can develop. These instabilities can lead to convective overturn. Convective overturn drives large-scale circulation patterns that influence where heavy nuclei appear in the envelope. Heavy element abundances in the envelope therefore do not reflect the initial composition at star formation, but reflect the cumulative effect of fusion and convective dredge-up. Because convective motions stir material across shells, nuclear burning does not occur in static zones, but in regions where composition evolves across time and space. In luminous blue variable stars, the interior thus behaves as a sequence of fusion-burning domains that advance through hydrogen-burning, helium-burning, and subsequent heavier element burning, with each stage releasing energy that supports the star against collapse, and that ultimately powers the radiative flux that emerges at the photospheric boundary. The interior chemical distribution evolves quickly, because extremely massive stars exhaust hydrogen in short fractions of their total lifetime. As hydrogen is exhausted, helium burning becomes the dominant energy source, and because helium burning produces carbon-nitrogen and oxygen abundances increase. Convective mixing transports some of those elements toward outer zones, altering opacity upstream. Opacity changes feed back into the radiative acceleration that drives mass loss, altering wind conditions. The fusion interior therefore influences outer wind behavior indirectly by altering chemical composition in atmospheric layers. Fusion of heavier species occurs in shells surrounding a more evolved interior core because as helium burning progresses outward, the core becomes dominated by heavier elements, while shells above it process lighter fuel. Fusion zones thus form layered structures in which hydrogen burns outside helium, burning zones, helium burns outside carbon burning zones, and so on. However, convection in extremely massive stars can mix these burning shells, reducing the clear stratification that might exist in lower mass stars. Waves and turbulence extend, mixing beyond strictly convective areas, and interior boundaries remain fluid. Changes in nuclear burning stage modify neutrino emission rates. At deeper layers, neutrino flux rises. Neutrinos carry away energy, almost freely leaving less radiation to support the outer layers. Because energy support influences how fast fusion proceeds and how long each burning stage lasts, neutrinos influence evolutionary timescales. In these extremely massive stars, the fusion interior evolves quickly towards states where iron group nuclei accumulate. At such high metallicities, the interior approaches the threshold at which fusion cannot continue to produce net energy. But this section concludes before addressing dynamical outcomes. Instead, it focuses solely on the properties of nuclear burning layers and their relationship to energy transport zones above, at radii greater than the fusion interior and energy transport layers, but still inside the larger cluster environment. The matter expelled by the star exerts mechanical, radiative, and chemical influence across local scales, and the effect of these contributions shapes the physical conditions in neighboring gas and dust. The continuous export of heavy element-enriched material through winds and the episodic release of larger mass parcels through eruptive phases both operate as drivers of feedback. Heavy elements released into these outflow layers increase the metallicity of surrounding gas and thereby change cooling pathways, because heavy element ions possess numerous transitions that increase radiative cooling efficiency. When the ambient medium cools more efficiently, its thermal pressure drops relative to gravitational binding forces, enabling collapse to proceed at lower density thresholds. Feedback from this luminous massive star therefore contributes to the regulation of gravitational instability by altering cooling timescales in the surrounding medium. Gas flows around the star adjust to these enrichment and pressure gradients, where pressure rises because of new mass injection, neighbouring gas parcels move aside, and where pressure falls because cooling has proceeded, matter converges. Radiation from the star maintains high ionization fractions in exposed regions, and these ionization fractions determine conductivity. Conductivity governs how plasma responds to magnetic fields, and magnetic fields influence how gas aligns along filaments. In exposed pockets where ionization remains high, gas remains strongly coupled to magnetic fields and flows along field-aligned directions. In shielded pockets where ionization fraction falls, gas decouples and flows along trajectories set by pressure gradients and gravitational curvature rather than by field geometry. Dust grains created in the interior outflow region contain heavy elements processed in fusion zones. When these grains mix with the surrounding medium, they increase dust to gas ratios. Dust grains alter the relative strength of energy exchange between radiation and matter, because they absorb energy and re-radiate it at longer wavelengths. They also provide surfaces on which molecules form, and these molecules contribute to cooling and to the chemical makeup of gas. Regions with higher dust density therefore cool faster and can achieve thermal equilibrium at lower temperatures. As shells from earlier eruptions propagate outward, they sweep up dust and gas. Swept matter accumulates along shell interfaces, compressing these layers. The compression raises local density and enhances shock formation, where shells encounter flows from other massive stars. Shock surfaces accelerate the mixing of newly enriched matter with older ambient matter. The mixture becomes chemically complex because gas from the stellar interior expelled through wind or eruptive mass loss merges with older gas in the environment. That older gas may have seen enrichment from other massive stars earlier in cluster history. The result is patchwork heterogeneity in metallicity on sub-parsec scales. Spatial variations in metallicity influence local opacities. Variations in opacity alter radiative acceleration in the surrounding medium. Where opacity is higher, radiation couples more strongly to gas, and radiation pressure can accelerate matter outward. Where opacity is lower, radiation pressure has weaker effect, and mechanical compression from shells or winds may dominate. The relative balance of radiation pressure and mechanical forces changes from place to place. Over time, these differences drive morphological diversity. Long wavelength propagation through this particulate network allows deeper radiative exchange between distant pockets of gas, because long wavelength coupling to grains remains weaker. This deeper exchange modifies thermal gradients, because parcels that would otherwise remain thermally isolated experience radiative exchange with their neighbours through long wavelength channels. The combined effect of dust composition, grain size distribution, metallicity, density distribution, and radiation intensity determines how rapidly or slowly matter reaches new equilibrium states. Zones of high density that become strongly cooled can gravitationally contract. Zones of high radiation pressure or high turbulence resist collapse and maintain extended geometries. The balance between collapse and dispersal depends on the relative magnitude of mechanical energy injection, radiative heating, radiative cooling, and magnetic tension. In the medium surrounding the luminous massive star, these forces operate continuously. The wind zone exports kinetic energy. The photosphere exports radiation. The energy transport layers supply the radiative flux. The fusion interior supplies new heavy elements. As these products move outward, they alter thermal, dynamical, and chemical characteristics of the surrounding environment. The fact that heavy elements accumulate in the surrounding medium increases opacity not only locally but globally across the enrichment footprint. This contributes to long-term changes in cooling curves of the cluster interstellar medium, and these changes influence the future ability of gas in the region to collapse into new stars. Enhanced cooling in enriched gas lowers Jeans mass thresholds. Jeans mass thresholds determine the minimum mass needed for collapse. Lower thresholds increase the probability that smaller mass clumps will collapse. Therefore, chemical enrichment from this star alters long-term cluster evolution by shifting the conditions under which new stars may form. The distribution of this enriched material depends strongly on the directionality of wind flow, the geometry of eruptive episodes, the orientation of magnetic fields, and the velocity shear patterns of ambient gas. Enriched material therefore does not disperse uniformly. High metallicity pockets form in arcs or ridges where shell compression was strong. Lower metallicity pockets survive in regions where mechanical impact was weak. Turbulent diffusion spreads these differences outward, but diffusion is not instantaneous. Local extrema persist across multiple dynamical timescales, where enriched material interacts with winds from neighboring massive stars. Secondary compression may concentrate matter further. Where feedback from other stars opposes this star's mechanical contribution, cavities may form that deflect enriched material along new trajectories. This star does not act in isolation. It interacts with a network of other luminous high-mass stars within the Quintuplet Cluster. Their respective windshells collide, shear overlap, and carve new channels. Chemical, radiative, and mechanical feedback from this luminous star therefore participates in cluster-scale feedback ecology. The contribution of this star to local enrichment does not determine entire cluster evolution alone, but it forms one node in a coupled feedback lattice. The feedback layer described here constitutes a distinct structural domain in which matter from the star influences the cluster environment around it. The measurement of physical information within this environment relies on methods that exploit electromagnetic energy, transport channels that remain functional within particulate-rich regions, and therefore wavelengths in the infrared become critical because particulate interaction cross-sections decline when wavelength exceeds typical grain dimensions. Infrared-capable instruments receive long wavelength radiation that has propagated through dust-laden media and conduct spectroscopic decomposition of that radiation into constituent frequencies. The spectral distribution contains information about temperature ionization, state molecular content dust composition, and density, because emissivity and absorption vary according to physical conditions in the emitting or absorbing medium. Emission lines from ions trace temperature and chemical composition. Continuum emission from heated dust grains traces grain temperature, and through modeling grain size distribution and composition, the mapping of this radiation across the region reveals spatial structure because differences in brightness across adjacent areas correspond to differences in temperature and dust column density. Infrared imaging therefore reveals filamentary gas structures, compressed shells, cavities, and ridges that remain undetectable in shorter wavelength channels. Infrared emission from partially ionized plasma reveals shock surfaces where energy has been converted into heat. Infrared emission from cooler dust reveals where grain populations reside within shielded pockets. Spectroscopic studies identify chemical transitions that indicate the presence of molecules inside cooler reservoirs and heavy element ions inside hotter regions. The physical interpretation of these observations uses radiative transfer models that incorporate dust opacity, gas opacity, and grain scattering. The models require assumptions about grain population size and composition because those determine opacity curves. When the curves are applied to measured spectral distributions, the result is a set of physical constraints on the emitting and absorbing matter. Long wavelength measurements produce maps of optical depth that indicate where dust columns are highest. Shorter wavelength infrared bands reveal where optical depth remains lower and energy escapes more readily. Spectral line broadening reveals velocity dispersion. In extremely crowded stellar environments, velocity dispersion reveals gravitational potential distribution because stars move faster inside deeper potential wells. Infrared spectroscopy can therefore constrain the depth of the gravitational environment and the density of stellar populations. The presence of heavy element signatures in emission lines reveals nucleosynthetic products in ejecta. The intensity of these lines indicates abundance. Abundance fields trace the degree of chemical enrichment. Infrared measurements also reveal thermal gradients, because different wavelength bands indicate different emitting temperatures. The combination of multiple infrared bands produces thermal maps that reveal stratification across Shell's wind zones and surrounding gas. By comparing intensity ratios across different lines and bands, physical parameters such as temperature density and ionization fraction can be constrained. These constraints do not specify individual observational vantage points. They specify intrinsic physical states within the region. If observational calibration changes, the underlying physics does not change. Infrared observations remain useful because extinction at these wavelengths remains moderate. Infrared radiation emanates from dust grains heated by radiation fields or mechanical energy deposition. Dust grains re-emit energy absorbed from ultraviolet and optical photons into longer wavelengths. Because these longer wavelengths propagate more freely through dust, they carry information about dust temperatures and indirectly about radiation fields. Infrared continuums reflect grain temperature distribution. Because grain temperature varies with proximity to luminous stars, infrared brightness maps reveal where radiative heating is strongest. In regions where grain composition contains ice mantles, absorption features appear at characteristic frequencies. Those absorption features identify specific molecules such as water carbon dioxide, carbon monoxide, or hydrocarbons. Molecular absorption lines reveal chemical composition of dust mantle material. In addition, thermal emission from gas reveals temperature in ionized regions. Infrared fine structure lines from ions provide direct temperature diagnostics that do not require optical transparency. Infrared spectroscopy can also constrain density through line ratios. When collisionality excitation dominates, line ratios shift. The shift reveals density. Infrared interferometry provides angular resolution beyond that achievable with a single aperture. Interferometry synthesizes a larger aperture and reveals finer spatial structure. In extremely dusty regions where optical imaging cannot produce resolved structures, interferometric infrared imaging can reveal morphology of wind-shaped cavities, shell boundaries, and filamentary ridges. Infrared imaging also reveals time evolution, because repeated measurements across intervals show movement of shell boundaries, changes in shock brightness, or variations in wind zone brightness. These variations reflect physical changes in mass loss rates or local density fields. Infrared data therefore form a time series record of dynamic changes. Information from infrared instruments becomes more meaningful when combined with radiative transfer models that consider dust opacity curves. Because dust mixtures vary across the region, these models require flexible grain size distribution assumptions. Grain populations change over time due to sputtering fragmentation and coagulation. The physical interpretation of infrared data therefore depends on dust evolution models. If grain size distribution evolves toward larger grains, extinction at long wavelengths decreases further. If grain size distribution evolves towards smaller grains, extinction may increase. Infrared observations must therefore be contextualized within grain evolution timescales. In extremely luminous star environments, these timescales remain short because feedback accelerates grain processing. Infrared spectroscopic analysis of ionization-sensitive lines reveals where radiation fields dominate. In those zones, ionization fractions rise. Ionization influences coupling between gas and magnetic fields. Magnetic coupling influences gas morphology. The interpretation of morphological patterns therefore includes magnetic field geometry. Far-infrared polarization mapping reveals grain alignment because elongated grains align with magnetic field lines. Polarization vectors reveal magnetic field direction. Magnetic field maps reveal anisotropic structure. Infrared polarimetry therefore connects dust grain geometry to magnetic geometry. This layered set of capabilities, spectroscopic decomposition, interferometric imaging, polarization, mapping continuum, fitting line ratio diagnostics, thermal emission mapping and temporal variability tracking, together constitute the primary observational approach to extract physical constraints from dust-rich environments. These infrared measurements apply to the shells, to the wind zone outer boundaries, to the cluster medium surrounding those zones, and when spectral resolution is sufficient to the outer atmospheric domain of luminous massive stars. They therefore form the measurement layer that permits physical constraints to be set on the internal states described previously. This completes the observational physics domain without entering cross-analysis of uncertainties associated with mass and luminosity estimates. At this depth in the structural path, a single massive star occupies the physical center of the layered regime described earlier, and this present moment portrait concerns that star as a luminous blue variable class object whose intrinsic luminosity lies in the extreme upper range for stellar sources in the Milky Way, with values that various extinction-corrected estimates have placed at levels that reach several million times the radiant energy output of an average main sequence star of solar type. The star exists within the particulate-rich medium of the Quintuplet Cluster, and within that medium its continuous wind zone and episodic mass loss history have produced shells of processed material that now reside at larger radii. The outer atmospheric layers currently define the boundary from which radiation emerges into the surrounding gas, and the high luminosity in these layers arises from fusion-driven energy that originates deep within the interior. The chemical composition in the upper layers contains heavy elements that have been dredged upward through convective and radiative mixing processes, and those elements influence opacity in line absorption transitions that modulate radiative acceleration. Because the star radiates intensely at its photospheric boundary, radiation pressure contributes strongly to pushing material outward. The continuous mass loss that results supplies processed material to the surrounding environment through a wind that carries carbon-rich and nitrogen-rich nuclei into the gas and dust fields beyond. Occasional eruptive episodes during prior intervals have produced more dramatic mass ejection events, in which larger quantities of envelope material were expelled rapidly, and those expelled layers contributed to the formation of the expanding shell system now present at radii beyond the wind zone. The star therefore participates in heavy element delivery to its surroundings not only through continuous outflow, but also through historical discrete ejections. The balance of radiation pressure and gravity in the outer envelope currently approaches regimes in which small changes in opacity can alter mass loss rates and modify wind velocity. This sensitivity contributes to variability because line opacities depend on ionization state, and ionization state depends on temperature. Because temperature varies when atmospheric layers respond to changes in radiative flux mass, loss rate variations arise naturally. Layered feedback between opacity and radiation pressure in this star therefore creates an environment in which steady outflow phases alternate with intervals of enhanced outflow. The shells residing outside the wind zone reflect the cumulative effect of these phases. Their existence indicates that the star has experienced previous mass loss episodes that exceeded baseline wind strength, and those episodes created compressed layers that now move outward through the local cluster medium. The stellar wind currently maintains an interface with the interior edge of those shells, and this contact discontinuity marks a region where momentum from the star-driven outflow transfers into ambient gas. The chemical enrichment inside the shells and in the wind zone contains signatures of the interior nucleosynthesis, because elements produced during helium burning and subsequent fusion phases have been transported outward. This enrichment alters cooling behavior in the local medium because heavy elements accelerate radiative cooling. Through that acceleration, enriched gas can collapse more readily under gravity if mechanical feedback from the star and neighbouring stars does not offset that contraction. This star therefore participates in the regulation of local star formation potential by changing the thermodynamic properties of nearby gas. The luminosity of the star remains extremely high in the present moment because energy released in the interior must cross the radiative diffusion and convective layers before reaching the photosphere, and because this star contains sufficient mass for radiation pressure to contribute significantly to its support against gravity. The interior fusion zones continue to process heavier fuels as central temperature increases, and the energy released in those zones drives the outward radiative flux. The outer atmospheric layers then modulate line opacities, and thereby modulate the coupling between radiative flux and matter. The wind zone then converts that coupling into momentum flux. The expanding shells then carry momentum into the surrounding medium. The current structure therefore represents a continuous chain from nuclear burning to mechanical export. Within this chain, grain formation begins inside cooling wind outflow, where seed particles condense and acquire mantles. These grains then join the particulate population of the shells in the local cluster medium. Grain size distributions therefore reflect both initial condensation conditions and subsequent processing in shocks. Dust within this environment influences energy transport, because particulate surfaces absorb energy and re-radiate it at longer wavelengths. Because grain populations contain enriched heavy elements, their optical properties differ from those of dust in more metal, poor outer galactic regions. When the star radiates energy into this medium, long wavelength channels allow that energy to propagate across extended distances, and radiative exchange across the particulate network conditions the thermal state of cluster material. In the present moment, this star therefore stands as a luminous engine that shapes its surroundings through energy, export, mass export, and chemical export. The physical parameters of mass, luminosity, and radius remain subject to uncertainty, because extinction models that correct for dust obscuration contain ranges of possible values. Dust opacity curves depend on grain composition and size distribution, and those parameters vary across the medium between the star and any distant point. Therefore, derived values for luminosity and mass contain uncertainties associated with the dust model applied. Nonetheless, all corrected estimates place luminosity in the upper extreme of known Milky Way stellar sources. The star resides within the deep gravitational field of the central galaxy, and within the dense stellar environment of the Quintuplet Cluster. In this environment, gravitational, chemical, radiative, thermal, and magnetic forces all interact. The star therefore exists not as an isolated object, but as one node inside a dynamically rich feedback lattice. The star influences the cluster medium, and the cluster medium influences the star through its effect on wind deceleration and chemical mixing in returned flows. The present moment configuration of wind velocity, mass loss rate, shell momentum, atmospheric opacity, interior fusion balance, and surrounding particulate density defines its state as an extreme luminous blue variable type stellar giant inside the central region of the Milky Way. This completes the portrayal of the star itself as a physical entity existing inside the layered structure described from the broad galactic context to the local cluster environment, and now to the single star domain, and this conclusion concludes the deepest structural layer without adding any interpretation about future outcomes.